All right, this lecture is going to cover Chapter 2, the first section, about kinematics. One of the things that we're going to be talking about here is how we divide ideas in physics up. And it's really important that you don't just dismiss it as quick vocabulary terms. It's how you're going to start thinking about relating these things to one another. So we're going to start with this idea of what we study, and pretty much what we studied the entire time in AP Physics 1 is mechanics. Alright, so what we mean when we say mechanics isn't the bits and pieces of machines or the practice of fixing the bits and pieces of machines, although those are related to mechanics. And when we say mechanics, what we're really talking about is studying the motion of objects and how that motion relates to the forces that caused the motion and the energy in those situations. So that means that more or less all of AP1 is going to be covering mechanics. In this chapter, Chapter 1 and 2, we're going to be Chapter 2 and 3, we're going to be studying kinematics. And kinematics is really just a description of how objects move. The word kinematics actually comes from the old word, I think it's a Greek word, kinema or cinema, and that's really just related to movement. Alright, so kinematics is more or less just the study of motion. Dynamics, which we move into directly after kinematics, is forces. Alright, so anytime you hear about the dynamics of things, dynamics usually makes you think of interactions, and dynamics are the forces and why the forces cause objects to move the way they do and how the forces cause the objects to move the way they do. And so it really makes sense, if you think about it, to first study what motion is and how to define motion and how to describe motion, and then talk about what causes them and why things move the way that they do. Which then will bring us into energy, which we'll get onto later. What I want to start us talking about really is translational motion. And translational motion is this idea of an object that moves without rotating. And believe it or not, there's not a lot of objects on Earth that do any sort of movement without motion. So translational motion, what I want you to think of is I want you to think of all of the motions that you do when you walk. Alright, so here's you. Good job, looking good today. Alright, and you walk in this direction. Alright, when you walk in this direction, if you think about plotting yourself against this, we'll say that this is 1 meter, this is 2 meter, this is 3 meter. Alright, what really happens to your whole body is first you go to point 1, and then you go to point 2, and then you go to point 3. And that's your translational motion. If we talk about what really happens as you go from point 1 to point 2 to point 3, alright, think about it. Like, your one arm swings forward, your other arm swings forward, you have one leg back, then you have the other leg back, and then that whole position changes, right? Then that leg swings forward and that leg swings back, and you end up in this other position, and you know, your arms are flailing all around. It really depends on how you walk and if you're good at it or not. Maybe even at this position, right, you've got a leg up in the air and this leg down, and you know, that arm goes there. And then maybe here, you know, you're standing, but then you bend over and you put your hands on the ground, and then you stand up, right? And you trip, and this leg goes way up in the air. There's all sorts of ways to get from point A to point B, but really in physics it doesn't do much good for us to, if we're trying to consider how you got from point A to point B or from point 1 to point 3, and we just want to analyze your motion. It's much easier to look at your translational motion, right? How you got to your final position. Alright, another way to look at this is consider, if you will, alright, a diver. Alright, this diver is moving with rotation. If we consider what they're doing, take a look at their arms and their legs. Like, their legs have to bend in order to launch themselves off of the diving board, right? And then once they're up in the air, if they're going to do any sort of fancy dive, right, they have to bend their knees here and curl their arms into their body, and then they're going to bend their body in order to make it down the hill, and they'll curl, and then eventually, to land in the water without doing a cannonball, they're going to have to stretch their body and their arms and their legs back out, and that's a whole lot of motion. There's a lot of rotating going on here. But what we really want to concern ourselves with, if we're going to talk about this diver, it's much more convenient for us to, instead of thinking about all of the things that the arms and the legs and the body did, is to think about just how they traveled from one point to the other. Alright, and this is translational motion. Alright, translational motion eliminates all of the extra motion, and it really just kind of makes it a straightforward analysis of how this person made it, the path they took to get from the diving board down into the water. This is translational motion. We will come back and we'll look at rotational motion, and we'll look at some of the finer details of motion. But first, before we can even begin to understand all of the excess, we have to understand how the whole body, the whole object, moved from point A to point B. What this would be, in fact, is this picture right here would be motion in 2 dimensions, right? We've got 2 dimensions here. The person is going to jump up and fall down. All right, that would be movement in the up-down direction. But this person also propelled themselves forward. So that means that this person is moving up and down and back and forth. Right? This would be motion in 2 dimensions, 2D. And we will go ahead and take a look at translational motion in 2 dimensions, but it's a little bit complicated, believe it or not. So it makes more sense for us to start with considering objects in just 1 dimension. So the first thing we take a look at before we look at 2 dimensions, which is chapter 3, we look at 1-dimensional translational motion, which is just objects that move in a straight line. That's all there is to it. So objects that move in a straight line, we could consider our straight line could be, right, walking in a straight line directly east, right, and it could be you. Here's you. Keeping it up, still looking good. As long as you move in only 1 direction, that would be 1-dimensional translational motion. Likewise, you could, instead of being moving up and down on this pathway, you could climb up and down a rope, and that would still be 1-dimensional motion. So as long as you're traveling in only 1 direction, it could be up a hill, right? You're still only traveling in 1 direction. It could be down a diagonal, still only 1 direction. So as long as the situation only asks us to consider 1 dimension, 1 line, it's 1-dimensional motion. And in order to do this, and in order for us to, instead of considering all of the bits and pieces, in order to consider just the translational motion, or what that motion, all of that back and forth and up and down, and all of that flip-flopping that occurred, we have to kind of more or less come up with a model. And so there's this joke that says a farmer is having a problem, and so he hires a physicist to help him. And the farmer says, I'm having this problem with my cow. Alright, and the physicist is going to consider the cow. And since you're a physicist, we'll be like, hey, look, this is you. Again, looking really good here. So you're the physicist and you're going to consider this cow, and you're going to help the farmer come up with a way to consider the cow. And as a physicist, you want to come up with a model to consider a real world object. And you say, well, you see, this cow is an awful complicated thing. And in order for us to really analyze it, let's reduce this cow. Instead of saying it's a cow, let's say it's a spherical cow. Right? And that may seem kind of silly to say we're going to consider, instead of an actual cow, a spherical cow. That might seem absolutely ridiculous, but let's consider this situation here. If we trade our cow for a spherical cow, right, there are some problems that it's going to be really helpful to answer. If we can reduce the complicated cow into a simple sphere, it might actually make it really easy to determine, say, for example, how many cows you could fit into a barn. Right? Then the spherical cow, which is much simpler to calculate the volume of, would be much simpler to determine how many of them you could fit into a space. For other situations, like how do you improve the milk production of a cow, this model is not so great. But reducing the complication of any object from, for example, a nice complex walking motion, right, where foot goes up, leg slings forward, knee bends, arm moves backward, other arm moves forward. This is a complicated system. So instead we say, imagine that this object is just a particle, right? It's the spherical cow idea. Right, if we reduce all objects to just a particle, then we don't have to worry about what piece is going where. We only have to worry about how this object moves from point A to point B, how the dot on this object moves along the way. So no matter what we're talking about in one-dimensional translational motion, you can treat it just as if it's a particle. Right? And that'll actually get you a pretty good understanding of the situation at hand and how an object's moving. So in this situation, if we're going to consider our cow, it's a good looking cow, right? If we consider that cow and we only want to figure out how that cow moves across one dimension of an axis, the idea of the spherical cow works out great. So we use the model of the particle.